Alright, so this time what we're going to do is we're going to use implicit differentiation to find the derivative of a curve which is not the graph of a single function. So at first we started off with nice functions, and then now what we're going to want to do is look at the unit circle. And so this is the equation x squared plus y squared equals 1. It's the unit circle which has radius 1 and centered at the origin 0, 0. So what this says is, I need a couple colors to do this, but so what this says is I have this circle fails the vertical line test, so there's no single function which would be the graph of this curve. But what I can do is split it into the bottom semicircle and the top semicircle and split this and locally solve for two functions. And then essentially what we're going to do instead is we're going to use implicit differentiation and pretend that everywhere we can locally solve. So locally on the top half we can write this as we can solve for y, and y will be the positive square root of 1 minus x squared. And on the bottom half we can locally solve for y of x as explicitly as a function of x as the negative square root of 1 minus x squared. So we can explicitly solve on the top and the half, we just can't globally do it. So what the idea of implicit differentiation does is it pretends that y is a function of x, and then we're going to differentiate with respect to x and then solve for dy dx. So regular terms that just have x, we do regular differentiation. Terms that have y's and x's in them, we have to pretend that y is a function of x, and then we're using the product and chain rule. Constant terms just get differentiated the regular way. So basically what we're going to do is find the instantaneous rate of change, so we can still find the slope of the tangent line at any point on the curve, but we'll have an implicit derivative depending on both x and y this time. What we're going to essentially do is, I like to view it this way the first few times you do this, and not be lazy. This is being lazy. The whole trick is we're pretending that y is a function of x. So at first, if you don't see it, write that in there, and then you can see this is going to be the chain rule: outside function, inside function. And this is why y prime appears in this one. So now what we're doing is implicitly differentiating this entire equation with respect to x. So first I use linearity to distribute the differential onto all of the terms. So this is d dx of x squared plus the derivative with respect to x of y of x squared, don't be lazy, equals the derivative with respect to x of 1. And then I use all my rules. When you have terms that were just x terms and don't involve y, it's regular differentiation power rule. This says that we're going to get 2x plus, we'll deal with this one last for a second, right now, equals, that we'll do the easy ones first. This one is derivative of a constant is 0. Now what I want to do is take the derivative with respect to x of a function y of x squared. So first I use the chain rule. Derivative of the outside, evaluate it at the inside, y, if you want at first, times y of x, times the derivative of the inside, which is dy dx. Now I've implicitly differentiated. Usually we don't write the of x, so I'll take that back out. You can write y prime also. This is Leibniz notation, which is much simpler and lazier a little bit. I like lazy too, but in certain contexts, especially when you're doing this, it's good to use Leibniz notation in my opinion. So I've now implicitly differentiated this equation with respect to x. Now what we have to do to find the derivative dy dx is solve for the unknown. In this case it's this guy. So we're going to solve for dy dx. So this is our equation implicitly differentiated, and now we want to solve for dy dx. Notice that a lot of the times this will happen in related rates and those types of questions too. When you set up an equation with a triangle, with a right triangle, you have everything x squared, and that's exactly what the circle had, was both the parameters were squared, so the 2 cancels on both sides. If you want, technically you should be safe every time and factor the 2 out. Then technically I'm multiplying both sides by 1/2. On this side it stays 0 and I get rid of the 2, so I got rid of the 2. Now, it's just like anything else. When I want to solve for something, that thing has to go to one side and then anything else has to go to the other side. So this is if and only if y times dy dx equals negative x. I bring the x to the other side, and then I divide, and this says dy dx equals negative x over y, assuming y doesn't equal 0. Notice the derivative now implicitly depends on both x and y, and so when you have to find slope of tangent lines or extra things in problems, you also need both the x and the y value to compute the slope of the tangent.